basically this wave equation. It's a function of two variables, t and x. X is supposed to be the u of tx is the position of the string at location x at time t. It satisfies this PDE with some boundary condition that string is tied at the boundaries, and it has this initial condition. And then if we try solutions of this special form where it's a function of t times a function of x, then we are able to get some special solutions, namely the sines and cosines with specific frequencies. So cos pi n t sin pi n x, sin pi n t sin pi n x, these were solutions. And so linear combinations of them are also solutions. And what we found is that by that method, by taking linear combinations of the special solutions, we are able to solve this for a lot of initial conditions. So, but question is, does it solve it for all initial conditions? And that becomes a question. If I have a function f, can I write it as a linear combination of sin pi n x? If I can do that, okay, then okay, there are a couple of issues here. So when I say can I write it as a linear combination? If it's a finite linear combination, absolutely no problem. If you can write your f as a finite linear combination of sin pi n x. Oh, sorry, I didn't. So did somebody start recording again? Okay, so somebody did. Good. Okay, so so if f can be written as a finite linear combination of sin pi n x, no problem. Then the corresponding linear combination an with ans of the solutions, namely something like this or this, will give you the answer to the problem. But if it's an infinite linear combination, there are multiple questions. Firstly, what does it mean for f to be this infinite linear combination? What is the notion of convergence here? Do we mean uniform convergence? Do we mean some other convergence, or is any of this sufficient? And then is it true that the corresponding linear combination is a solution? Is it differentiable? Does it satisfy the wave equation, etc.? So these are questions which led to Fourier analysis to see what functions can be written as linear combinations of sines and cosines. So here is the more general question. Given f from 0, 1 to r, can you write it as a naught plus summation a n cos pi n x plus sin pi n x? So as I wrote in my notes and in the chat, so in the notes I have written more other things. So instead of this, I started with a somewhat finite problem where instead of a vibrating string, we have n bodies connected by springs. Okay, that when n goes to infinity is what leads to the vibrating string actually. So I have written out an actual in the notes. I have written it out in that sense. So you have n bodies connected by springs. So where is the picture? Okay, where is the picture? There was supposed to be a picture somewhere. Okay, so the picture is like this. Sorry, picture is of some spring, and then there is a body. At the two ends, there are walls which are immovable. And so if you have these bodies with, let's say, all of them have the same mass and all the springs are identical. At rest, it is like this. Then you may pull the bodies to one side and so on and let it go. Then they will start vibrating. And what are the equations? So I have written that out. So that becomes, in x variable, it is discrete. So then there will be u1 of t, u2 of t, and un of t. And there is a differential equation in t for that. Okay, so basically you will get something like that. So instead of here, instead of this, you will get something like del square uk of t over del t square equal to, instead of there is no x variable to differentiate, the x variable is discrete. So what you get is a second difference operator. So let me write del square u k of t, where this means uk plus 1 of t minus 2 uk of t plus uk minus 1 of t. So that the x variable is discrete. So in some sense, this is a bit simpler. than the other one. But I also put in another one which is completely discrete. So let me just describe that. It's a different looking application. I mean, different looking motivation, but it is actually as relevant and important. I will not do it in detail, but I will just describe what is the other problem. So it is a problem from probability called random walks. So this is also just as good as a motivation. Random walk problem. So what is the random walk problem? Actually, what I have written is random walk on the cycle, but you can take random walk on integers also. Why is it going in some public direction? So here just let me write 0, 1, 2, 3, minus 1, minus 2, and so on. So what a random walk does is it starts at some place, origin, and at each time, so time is discrete, time equal to 0, position is 0. At time equal to 1, it will go either to position +1 or -1 with probability half each. And if it goes to -1, next step it will again go either to 0 or or -2 or 0 with probability half each, etc. I hope this is clear to everyone that at each step a coin is tossed, and if it is head you go one step to the right, if it is tails you go one step to the left. Okay, so and you keep tossing coins and keep doing this. So this is actually a simple problem, but I want to do it in the way that we did. So if it's not clear, you can ask me, but let me write what it is we are interested in. Let Pt of k be the probability that random walk is at location k after t steps. Okay, I hope it is clear what it means. So after t steps, t is discrete here. Okay, after t steps, what is the location of the random walk? Now you can write a very simple combinatorial binomial formula for this, but the point is there are other problems similar to this with slightly more complicated settings where you can't write it. So I will also write a complicated solution to this problem. I won't write the problem. I will not write a combinatorial answer. We'll get to that at the end. But so the question is to determine this goal. So to solve the random walk for me at the moment means that to find what is the probability distribution after time t. So after 100 steps, what are the locations where it is going to be and what are the probabilities? Okay, so let me emphasize again, this particular problem is combinatorially very simple. You can write a simple binomial formula, which we will come to at the end. But what I want to convey is the method. Okay, so this is very similar to the earlier problem. So how? Let me explain. But before that, is everyone clear about this? So some of you may not have seen it before. I don't know if everyone has seen random walks before, but if it's not clear, I'll be happy to explain what the problem is. Is it okay? Okay, so I assume it's okay then. So what is it that, how do we solve for this problem? So here is the equation for PT. Equation for PT of k is that what's the probability at time t plus 1 I am at k. Okay, it is for me to be at location k, so k is somewhere. I have to be here at time t plus 1. So previous step I must have been at either k minus 1 or at k plus 1. So there are two ways. I must have been at k plus 1 and come here. So that means at time t I was at location k plus 1 and I have to, but that's not enough. If I make a step to the right, then I won't come to k. I have to make a step to the left. So that probability is 1/2. Or I might have been at location k minus 1 and I made a step to the right like this. Okay, so this is the equation for the random walk. This is true for any t greater than equal to 0 and k integers. Okay, so we will write this in a slightly different way. So this is the main equation, but let's just reformulate so that it looks somewhat similar to what we had before. It's not quite the same. I will explain. So let's subtract pt of k from both sides. So then if I pull out a half here, what I get here is pt of k plus 1 minus 2 pt of k plus pt of k minus 1. Okay, so this looks very similar, somewhat similar to the other one. What is it? So here we have, this is the first difference in t variable, right? So pt plus 1 minus pt, first difference in t. This is second difference in k. See, first difference would be pt of k minus pt of k minus 1. So you take difference of two of those at k plus 1 and k, then you get this. So that's what I mean by second difference. So if you apply the difference operator twice, you get this. So this is telling that the first difference is like second difference. So it's not quite like this. It's not like this where you have second derivative, second derivative. What is the continuum analog of this? Continuum analog of this is the discrete analog of if you make both t and k continuous variables, call it t and x, then you get del u del t, because left side is single difference, equal to 1/2 del square del x square u of tx. So you may have seen this equation too. This is called the heat equation. Another very important PDE, second order PDE. So it's not the wave equation. Wave equation has two derivatives in t and two derivatives in x. Here it is heat equation, one derivative in t and two derivatives in x. But our motivation wise for Fourier series, this is just as good. So let's not do the continuous case. You can do the, I have left it as exercise to take this equation and do everything I did for the wave equation. What all I did for wave equation, do it for the heat equation, meaning try a separation of variable solution, find special solutions, then you arrive at the same question of Fourier series, which functions can be represented as this. Okay, I left that as exercise in the notes. But here what happens, this is a discrete situation. So we can solve it exactly like earlier, meaning, so I have written it in the notes, so I won't spend too much time, but I will just, let me just quickly explain what happens. So like before, we will try a solution. By separation of variables, pt of k equal to v of t times w of k. Suppose I try a solution. So what do you get? On the left side, you get v of t plus 1 minus v of t times w of k. Right? Equal to 1/2. Here the t variable is constant, so v of t comes out. And what I get is w of k plus 1 minus 2w of k plus w of k minus 1. So or if you write, separate the t and so v of t plus 1 minus v of t over v of t. Don't worry about zeros, just do it. W of k plus 1 minus 2w of k plus w of k minus 1 divided by 2 times w of k. Now this depends on T and this depends on K. So what must be the case? They must both be constant. So there must be a lambda such that these are equal to minus lambda, right? Minus lambda in anticipation that it will turn out to be negative. So lambda will be positive. Okay, so now you have to solve these things. So the equations for W, if you fix W, you get W of K plus 1 minus 2W of K plus W of K minus 1 equal to minus 2 lambda W of K. And V of T plus 1 minus V of T equal to minus lambda V of T. So these are actually what this is if I have written there for the in the notes, I have written it for the space is not integers but the cycle. So what I have written there is for something like this 1, 2, 3 up to there are n locations, in which case this K will be actually only n values. The space location is only n values. Time goes from 0 to infinity. So there, but idea is similar, but it's a bit simpler when it is finite because it becomes a finite number of equations. So this is actually an eigenvalue equation. So if you think about this, this is, you put what this is actually if you transfer this one. So you have 0, 1, 1, 0, 1. Okay, it goes on. In this case, it goes on forever. It's an infinite matrix. So we can write it like this. So formally, there is an infinite matrix multiplying an infinite vector. And what you are supposed to take, I am transferring this to that side. So I get 2 minus 2 lambda times so it's an eigenvalue equation, looks formally like an eigenvalue equation. When you actually take finite space, you actually get an eigenvalue equation. What I have done in the notes is find all the eigenvalues and eigenvectors of this. That fixes the values, possible values of lambda for you, and also gives you a solution for WK, because you get each eigenvalue eigenvector will give you one solution for lambda and W. And you take that particular lambda and then you can solve for V, because V of T plus 1 is just 1 plus lambda, 1 minus lambda times V of T, which means it is 1 minus lambda to the power T times V of 1. So you can solve for V of T once you have lambda. So this way you get a solution, you get a finite number of solutions in the finite case. Here it is many solutions, but let's take the finite case. Then you have n solutions for lambda and W. Each of those lambdas will give a solution for V, and you get this. And then for you can solve for PT. What is supposed to be PT? But the main thing is that this particular solution will not satisfy the initial condition you want. This will satisfy at time t equal to 0, you will get V of 0 times W of K. But if you think of the original problem, what I want is that the initial condition P0 of K should be 1 if K equal to 0 and 0 if K not equal to 0, because I'm starting the particle at the origin, or here I may start it at 1. Okay, or maybe you call it 0, 1, 2 up to n minus 1. So, okay, so you start the particle at a particular point. So at time 0, it is at that place with probability 1 and elsewhere with probability 0. So initial conditions are this, not what I get out of these equations. But now the thing is, these eigenvectors will form a full basis for Rn. Therefore, you can write this initial condition 1 at 0 and 0 elsewhere. You can write it in terms of these eigenvectors, and consequently you can solve exactly for P. So the question of Fourier series does not quite arise here, in the sense that you can write the question that was here does not arise because everything is finite. You can actually write your solution in terms of the eigenfunctions and you can get the solution. So, but if you go to the infinite space situation, then you get a similar question whether we can write our initial condition as a infinite linear combination of these special solutions for W, namely there will be some sines and cosines. Okay, so that's what is the thing that is written there. Yeah, I am not actually going to write the details, but if somebody wants, I can go a bit more over this. So, are there any questions or was I clear about this? Any questions, comments on this?
For this particular infinite matrix, is there a reason to expect the functions to be sines and cosines, as in the eigenvectors and eigenvalues?
Yeah, it's a good question. So what are the eigenvectors? So the thing is, it's not even clear what exactly it means, but formally, yes, formally I can show you. So so the finite case is worked out in the notes, but here basically, sorry. So you want so suppose you take this matrix. Oh, sorry, I forgot to write the dots. Formally multiply by this, where you have e to the I theta, e to the minus I theta, e to the minus 2I theta, okay, e to the 2I theta, and so on. What do you get? In the kth row, I mean, so okay, so when you multiply that, so what do you get? I mean, so you get in the kth location, so let's take kth location. What we get is, we get 1 is multiplying the previous one. The diagonals are 0, 1 and 1 on the off diagonal, right? So you get.
Right, you basically get this thing multiplied by cos in this case.
Yeah,
to
you
cos
get
theta.
I k minus 1 theta plus e to the I k plus 1 theta. Exactly, like you said, which is again e to the I k theta into 2 cos theta. Because you get e to the I theta plus e to the minus I theta. So, in some sense, it's exactly the same vector we get. So, it's like this vector is eigenvector with eigenvalue 2 cos theta. For all theta. So, there are uncountably many, for every theta in 0 to 2 pi, you get a, or we can take 0 pi because that will give the same, right? So, we can take 0 to pi maybe. Because cos of minus theta is same as cos theta. No, but the eigenvector is not the same. So maybe I write 0 to pi. So anyway, you get these eigenvectors, so to speak, formally, because we don't know what is the, you have not studied, and it is not an, it is the subject of functional analysis to make sense of what these things can be. I mean, what it means, eigenvector, eigenvalues in infinite dimensional situations. Which is why I wrote the finite dimensional situation. Here you will get a finite matrix, n by n matrix. So eigenvectors, eigenvalues are very clear. You get n eigenvectors and eigenvalues, not infinitely many, n eigenvectors, eigenvalues. And they will also be like, they will be exactly these type of vectors, but for specific thetas. There will be n values of theta, basically the equispaced ones, 2 pi by n, 2 pi by 2, I mean, multiples of 2 pi by n or something like that. You'll get n equispaced values of theta for which there will be eigenvectors. Okay. So, but formal, this is a formal statement. Okay. Formally means, yeah. So as I keep saying, I mean, there's sometimes people get confused formally because I mean, the word formal is used, to my knowledge, in when you wear clothes. So you go to a shop, you ask for casual clothing and formal clothing. Actually, the meaning is quite the opposite in mathematics. Formally means you just follow the form without the content. Okay, so it's, well, it's not the opposite meaning. It's the maybe the same meaning. Formal clothing is maybe where you want to have a nice form, not necessarily content. But formal. So formal doesn't mean more, but usually people think that formal means more, somehow more rigid. But actually, formal in mathematics means you are just following rules without asking whether it makes sense. So you are following formulas. So this is a formal analysis. So it's not clear what eigenvector eigenvalue means. Okay. So that's why the finite tree situation is better. I recommend you to read that in the notes. And then I work out exactly the PT of K. It comes out to be some binomials in the case of this finite tree thing, the sum of binomial coefficients, which can be done also combinatorially. Any other questions? So I hope it answered your question, what it means eigenvectors. This is the meaning.
Yeah.
Any other questions? Okay, so then let me proceed. So motivation is done. Okay, so yeah, in some sense, so in doing this, I use one thing. So here I often sometimes I say the most important. So this is actually will be the running theme. So one of the running themes in the course will be that discrete situations are as interesting as continuous situations. For me, this equation is as interesting as this PD. I mean, it somehow happens that in mathematics, people studied these PD things before, but finite things maybe later. But in the recent past, more and more people are studying these things with motivations from theoretical CS and various other things. And the analysis actually is very similar. Okay. Secondly, another nice thing about the discrete situation is technicalities are minimized. As I said, when I go here, there is no differential equation. Everything is finite. We have eigenvalues, eigenvectors. It all reduces to something we can do by hand, elementary. I mean, it may not be easy, but the framework technically is easier. But when you go to differential equations, you have to talk about smooth functions, you have to talk about derivatives, whether derivatives exist, etc. All sorts of complicated things come in. Okay. So similarly, when you have infinite series, what kinds of convergence you have, okay, all those things come in. But finite situation, you get all the same in spirit, but without the technicalities. Okay, sometimes you lose something, some symmetries are lost, but anyway, that's the difference between discrete and continuous. We will care about both. That is one of the themes that you have to be aware of in the course. We'll constantly move between discrete and continuous. We don't care. Second is, so let me come. So what is actually going to happen in this course? Okay, so what's going to happen? So I'll tell you. So the most important identity in analysis. Okay, so what is the most important identity in analysis? Anybody has a vote for something? Okay, of course, such a thing question doesn't have any sense. I mean, so it's a question of what you think. So what do you think is the most important identity in analysis? Anyone with opinion?
E raised to I pi.
Okay.
That one probably.
Okay. So you have a proposal e to the I pi plus 1 equal to 0. So this is Euler's identity. Okay, before you make sense of that, we have to have independent meanings for all this. What is e power z? I mean, we have to have one we know, I is the solution. I is the solution to I square plus 1 equal to 0. Okay, so that is fine. E power z by definition is z to the n over n factorial. And what's the definition of pi? One can take many definitions of pi. Let's go for the definition that it is the length of the, I mean, 2 pi is the length. So pi is the length of the semicircle. So which means it is 0 to 1. Or what is it? Sorry, pi is the area of the circle, right? So what do I want to do here? So if I take this, yeah, I think it is 1 by square root of 1 minus x square dx. Is that correct? Maybe 2 times that. So that's the definition of pi. So with these two definitions, everything is here is defined. Then you have this amazing identity e power I pi plus 1 equal to 0, which Euler proved. Okay. So of course, all these are independently defined, and then it's amazingly solves this. So somewhat recently, there was a funny study by, so there's a neuroscientist called Samir Zeki. So he teamed up with a famous mathematician. So Samir Zeki, he teamed up with a famous mathematician, Michael Atiyah, who passed away quite recently. One of the most famous, very great mathematician. So they wanted to. So Samir Zeki is a neuroscientist. He was studying aesthetics, how it is coded in the brain, whatever it is. So right. So they were studying aesthetics in art as well as. So he wanted to also study what people think when they think of beauty in mathematics. So with he teamed up with Atiyah, and they had some 25 equations or identities, and they showed various mathematicians and took a survey of what people think, which ones are beautiful, which ones are ugly, and to rank them by beauty and so on. So you can have a look at that. It's kind of fun. I don't know whether to take it fully seriously or not, but so this one came out to be tops. Okay, so most beautiful. So most people thought it was most beautiful, whatever be the reason. Okay. So anyway, so what this is saying in geometrical terms is that e power I pi is -1. Okay. So a generalization of that would be, that's not what I want to say. So this is saying that the e power I pi is -1. So 1 and -1 are the two roots of unity. So if I take e to the 2 pi I k over n, k equals 0 to n minus 1, I get, what do I get? Okay, sorry, I get 0. Why I wrote. So for n equal to 1, 2, 3, and so on. Okay, so this is saying when n is 2, this is okay. So sorry, not n equal to 1. To the 2 pi I, n equal to 1. Does it make any sense? So when no, sorry. So n equals 2, 3 onwards. Something is a bit fishy. What did I do? Right. Okay. Yeah, sorry. So when n is 2, 3, and so on, e to the 2 pi I k by n is actually 0, right? So you agree. That is, so when n is 2, that is this identity, but this is the more general one. In fact, so a little more, so in fact, so let me write that a little more, slightly more complicated way. If you take e to the 2 pi I j times k over n, and I sum k equals 0 to n minus 1. I have introduced an extra factor j here. So what do I get here? So the answer is 0 if 0 or n if j equal to 0 mod n, and 0 otherwise. So what happens is basically, so this you see, it's actually a general, so this the same thing written in a different way. When j is, let's say, you don't have to look at, you just look at j equal to 0 up to n minus 1, right? When j is 0, all of these are 1, so you add up, you get n. When j is 1, you go over all the nth roots of unity, you get 0. And when j is 2, and 3 and so on, you go over some roots of unity. It may not be all the nth roots of unity, but you will, if for example, if n is 4 and j is 2, you will go only over the second roots of unity, right? So something like that. But anyway, this is a very important identity, which is a generalization of this. This is true for all integers. Well, the way I have written, it is for actually, sorry, for all n is just a positive integer. When n is 0, is it okay? Yeah, this I can write even for n greater than equal to 1. Because when n greater than equal to 1, yeah, anyway, that's okay. So everything is 0 mod 1. So now this is in fact a very important identity. Further, if I divide by n and let n go to infinity, setting sorry, what is it I want to do? Yeah, I'm summing over k, right? So yeah, what I get, let me write it. What I want to write, e to the 2 pi I j theta. So k over n. So if you divide by n, k over n, it's like a Riemann sum, right? So if you look at 1 over n, e to the 2 pi I j k over n. So this is like a Riemann sum. So what happens? It becomes the integral. K over n becomes the continuous variable theta, and you get e to the 2 pi I j theta d theta. So this is for all j in integers. Both positive and negative are fine. So this is actually going to give me what? It will give me, so you are dividing by n, so it will give 1 if j equal to 0 and 0 if j is not equal to 0. Okay. So that's what you get. So for any j not equal to 0, when n is very large, j is not going to be 0 mod n, means j is 0. So this is true for every, you can verify it directly. You don't have to come from here, but it is, I am just relating it to this. So one of you pointed out this is a beautiful one. From there we get this sums of nth roots of unity is 1, and from there you get this identity. This is what I call most important identity in analysis. In fact, this entire course is going to be actually exploiting this actually. I mean, there will be many concepts, many things that we will do, but at the heart of it, we are exploiting this identity again and again and again. That is actually the heart of the. So this you have to keep in mind as you go through various applications, what all we do. This is what will happen. I mean, we will be using this identity time and again. E to the 2 pi I j theta d theta is 1, integral is 1 if j is 0 and 0 if j not equal to 0. Okay, so this is not some, it's yeah, so this is going to be a running theme through the entire course. Okay, so now let's come to further, let's go further. Any questions, comments? Yeah. Any questions, comments? No?
So the
Okay.
limit integration should be 0 to 1. I think.
Ah, you're right. Yes. So I already put the 2 pi in the exponent. Yeah. Thank you. So the integral is 0 to 1. So later, I mean, I will probably be writing in the form e to the 0 to 2 pi e to the I k theta d theta is going to be 2 pi if k equal to 0 and 0 if k not equal to 0. K integer. If I don't write 2 pi in the exponent, it will come to this form. It's the same as the other identity. Okay. So there the integral will be 0 to 2 pi. Thanks. So that's here it is 0 to 1. Okay. So this will be this identity will come time and again, and it will be it is actually the important point actually. So it is okay. Anyway, so now let me start the subject sort of, but again there is a little bit of motivation involved. So let's maybe I just do it here. So what is this? So I gave some motivation. Some of you have seen it before also. Fourier series and Fourier transform. You may have seen this. So Fourier series involves writing f from t to complex number. T is actually the unit circle. So you can think of it as unit circle, which is also same as 0, 1 modulo the equivalent 0, 1. If you take the interval 0, 1 and identify 0 and 1, you get the circle. You can think of it as R quotient integers. If you take R quotient integers, all these are the same thing. That is what I call T. T for torus, well, circle, but when you take higher dimensional ones, it becomes torus. So we call it T. Writing a function from T to C in terms of sines and cosines. So here k greater than equal to 1, k greater than equal to 0, cos k theta. So this is what it is, which is equivalent to, like Nishant asked last time, in terms of, instead of we will now onwards not be writing in sines and cosines. It's much more convenient to write in terms of complex valued exponentials. So let's call it ek. Ek of theta is e to the ik theta. So for k in z. So from ek and e minus k, you can get cosine k theta and sine k theta and vice versa. So you can get from here and there. Okay. So the question is of writing the function f in terms of these complex exponentials. Okay. That's kind of what we did, right? I mean, that was the motivation. Can I write a function from 0, 1 to r in terms of this? So here it was a function on 0, 1, but we can think of it as 0 and 1 with 1 identified with 0. I mean, so, well, okay. So anyway, so don't worry about that point. So function on 0, 1 to r, we wanted to write in terms of sines and cosines. There I had written pi and x, pi and y, but here let's write it as 0 to pi. I mean, so t for me is 0 to 2 pi. Yeah, so it's maybe I will also use 0 to 2 pi. That's the more common one. So I won't put 2 pi in the exponent. So it is e to the ik theta. Okay, so the question is, can I write a function in terms of this? Fourier transform, if you have seen. If you have not seen, it's okay. In Fourier transform, you may have, so some of you may have seen it in terms of, if you have taken probability courses, you may have seen characteristic functions, which are the same thing. So here it is writing a function on real numbers. Function is now not on t, but on real numbers as in terms of complex exponentials. But now we are not restricted to z. We take e lambda of x equal to e to the I lambda x. Okay, for lambda also comes from real numbers. So basically, well, I write in terms of, so here it's a somewhat one has to be a bit more clear what is in terms of. So you may write it as continuous super. Now we had countably many. So you try to write f as a sum of those things, I mean possibly infinite sums. But here you have a continuum of those. So you may write things like fx as a superposition of this, meaning some a of lambda, e lambda of x, d lambda. So it is not a sum anymore, but possibly an integral, but it's nevertheless a superposition, linear superposition of these complex exponentials. So that is the problem of Fourier transforms. We'll come to these things. We will define Fourier series, Fourier transforms properly later, but for those who may have seen, probably everyone has seen it in some way or another before. That's why I'm giving this as motivation. So what is it I want to take from here? So the question I want to ask, assuming that you have seen this or now you have seen this. So the question is, what are these special functions in terms of which I am writing? What are ek for torus or e lambda for real numbers that we are writing trying to write in terms of them? We are trying to write a general function in terms of ek's or e lambdas. Why? I mean, what is special? What has ek to do with the torus, or what has e lambda circle? E lambda, what has e lambda to do with the real numbers? That is really the starting point for me. So the answer is. So what is the answer? Anyone knows already? What is ek or e lambda? Some of you might know.
Eigenfunctions of the Laplacian, something like that.
Okay. Yes, it is. It is true. They are functions, but I will come to that later. A different answer.
A basis?
Huh?
Like something like a basis?
Well, that is what we are trying to ask. Do they form a sort of basis? Well, we have to make sense because we are now in infinite dimensional situation. What is a basis? That is what we are going to ask. But why in terms of this? I could look for any basis. Why these functions?
These are characters for the group.
Okay.
For the
so somebody says,
these are the irreducible representations or the characters. Yeah.
Okay. So they are the characters. Yeah. That's correct. Okay, so now let me define what are they actually. So the torus is a group under multiplication. So best is to think of torus as e to the I theta 0 less than equal to theta less than 2 pi. Okay, so think of the torus as this. It is the unit circle in the complex plane. One is here, e to the, so think of them as e to the I theta, where theta goes between 0 and 2 pi. So this is a group under multiplication. R, of course, is a group under addition. Okay, I assume everyone knows the definition of groups and so on. At least it will be necessary. I'll have to assume that. So these are groups. They are actually abelian groups. They commutative. So what is E lambda? So E lambda is, so if you look for E lambda has the property that E lambda of x plus y is e to the I into lambda into x plus y. But that is e to the I lambda x, e to the I lambda y, which is E lambda of x times E lambda of y, right? So E lambda is a map from R to C, or R to C is a homomorphism. Okay, sorry, let me not write C, let me write here T. It's not C with addition, it's C with multiplication, but okay, so, or maybe Yeah, should I write? Yeah, so it's a homomorphism. Okay, so that is homomorphism definition is precisely this. E lambda of x plus y should be E lambda of x. Here we have writing the group as multiplication, so it's E lambda x times E lambda y. So this is a homomorphism. So a small exercise. These are all the continuous homomorphisms from R to T. Okay, so T is a group. So these are all the continuous homomorphisms from the real numbers into this unit cell. Okay, so this is a familiar problem, by the way. What is so you have a function f from R to T. If it's a homomorphism, it means f of x plus y equal to fx into fy. You have seen this kind of problem. If fx plus fy is fx plus fy, is it linear? Is it here it's multiplicative, so is it exponential? So we are mapping into torus. So in general, it's an exponential. You need a little hypothesis. That's where the continuity comes in. Okay, so you probably everyone has seen this kind of problem. If not, we'll be happy to discuss later. Okay, but think about it. Can you show that any continuous homomorphism from R into T has to be of the form e to the I lambda x? It's one of the E lambdas. Okay, so okay, what about here? So now I look at Ek from T to T is a homomorphism. Right? So what is actually, it's a little confusing. Okay, so actually this confusion I'm never going to clear. I got the torus like this. Actually, it's a bit maybe yeah. So we will write like that, but it is also as the 0 to pi with addition modulo 2 pi. Okay, you take the 0 to 2 pi with addition modulo 2 pi. That is the same as this. So I'm going to confuse the, I mean, the notation will be sometimes confused because I will write here ek of theta plus phi is exactly like before e to the ik into theta plus phi, which is a product which is ek of theta, ek of phi. Okay, so it is a homomorphism, but what the confusion I'm talking about is on the left side I use t in this notation. I use 0 to pi. I am writing the elements as theta and phi. On the right side I am writing it as e to the I theta. Okay, so I hope you will get used to this yourself. I mean, there is nothing very confusing about it, but sometimes I like theta and phi. Sometimes I prefer multiplicative one. So just because yeah, so if we want to write in complex, I mean with multiplicative notation, it's not ek but z going to z to the power k. Right, ek of, if you want to write in terms of multiplicative notation, it's not exponential but z going to z power k. That's what the ek is. But I want to write always this complex exponential notation, so slight confusion, but it's okay. Again, a small exercise. These are all the continuous homomorphisms. From T to T. Okay. So that's what these exponentials are. They are continuous homomorphisms from the group of interest into T. Okay. Any questions so far? So here, when we think of 0, 2 pi modulo 2 pi, it is important that 0 and 2 pi are equal. So that's why E lambda doesn't work. Okay, because E lambda of 0 will not be equal to E lambda of 2 pi. So if for me to get a function on the torus, it has to be, if you unwrap it, it has to be 2 pi periodic. So E lambda of 0 has to be E lambda of 2 pi. That's why I have to take lambda to be an integer. That's why Ek, K in Z. Okay, Ek, these are the only homomorphisms. E lambda for general lambda is not a homomorphism. Although it might look like it's satisfying this, it's not a function on the torus. Okay, any questions so far? So one question here is why, okay, fine. These are two groups we were interested in, T and R. But why homomorphisms into the torus? So these two should be separated. Here, the T as domain and T as target should be separated. We will always look for homomorphisms into T. Okay. For a moment, let me not answer it.
It's 1 o'clock.
So let's not answer it. For some reason, we keep the target as the torus, as the circle, unit circle. For now, let me just leave it. Let me not try to answer it. Maybe at some later time, I will give some answer. So the question is, can we do it? Oh, okay. So it's time. So what we will do now is go to other groups. Next is. Can we do the same? Can we look at functions, homomorphisms into the circle, and what will they give us? Okay, so we'll do that. Okay, I'll stop here. Sorry, I said I'll stop a couple of minutes before. I didn't notice. Okay, but I will stay. If there are any questions, I'll be happy to answer.